Welcome to UppTalk. My name is Maja Garde Lindholm, and together with my colleagues Anneli Björkman and Nina Lund, we meet researchers from the Faculty of Science and Technology at Uppsala University and talk about current research. During the autumn, we will broadcast 2 talks a month on Tuesdays at 12 noon. UppTalk is organized by the Faculty of Science and Technology to give our alumni and anyone who's interested an opportunity to take part in the exciting work conducted at our university. We are broadcasting live from the recording studio Blåsenhus here at Uppsala University, and you who are with us live here today, you have the opportunity to ask your questions directly in the chat. So send your questions to me. I will see them on my phone here and include them in the conversation. I would also like to mention that this conversation is being recorded and can be viewed afterwards via Uppsala University's YouTube channel and on our webpage. Robot technology is progressing fast, but there's still big challenges making robots and prosthetic hands have a sense of touch, similar to us humans. This would make them safer and more useful, and the technique could also be used in other medical applications. So what does the latest breakthrough bring that can make this possible? We will discuss this with today's guests, researchers Zhibin Zhang and Assistant Professor Libo Chen, who work on flexible electronics and neuromorphic engineering at the Department of Electrical Engineering. So a warm welcome to Zhibin and Libo. So let's start from the beginning. Can you tell us a little bit about yourself and why you choose to do research in your current field? Maybe you can start.
Okay. Hello, everyone. My name is Zhibin Zhang. I'm happy to be here. I'm currently a researcher at the Uppsala University, and I'm leading a group, the FANET group. So our research focus is on flexible electronics and neuromorphic engineering. So, and myself, I originally came from China to be a postdoc researcher in the beginning at the KTH, the Royal Institute of Technology. I worked there for 8 years. And then I joined Uppsala University in 2011, and so it's quite a long time. And my research expertise is specialized in basically flexible electronics using cool materials like carbon nanotubes and graphene. And then some years ago, when Libo joined my group, we started to expand our research area to encompass neuromorphic engineering.
Neuromorphic engineering. What is neuromorphic?
Neuromorphic engineering is actually an approach that apply the principles our nervous system use.
Okay.
Right. So I believe this is a powerful approach to advance the flexible electronics for wearable devices that apply on body, so get the benefits for human beings.
Okay.
Yes, thank you, Maja. And my name is Libo Chen, and my PhD study is mainly about develop smart sensors to meet the challenge in the area of Internet of Things and artificial intelligence. When I joined Zhibin's group in 2018 as a postdoc, we decided to do some research on artificial tactile systems to empower the prosthetics and robots with a human-like sense of touch. And now I'm an assistant professor at the same department, and our research is mainly focused on neuromorphic circuits and the system, as Zhibin mentioned. I chose this, doing research in this area because I believe that mimicking the human's nervous system is the most promising way to enable the AI agents like smart robots and AI-powered drones and electrical vehicles to have the ability to interact with the real world like humans with a similar performance and energy efficiency.
So the development of robotics is moving forward really fast. And we see many new applications for robotics and robotic prosthetics, for example. Can you give us a few examples of what's...
Yeah, sure. This is very interesting. You are right. How robots is used in social services, like prosthetics, really depend on what kind of new functionality we can give robots, right? So, for instance, take the fact that now the population of aging people is growing very fast, and more and more people ultimately will lose muscle strength. They can be disabled when they get older. So in this case, I mean, in the future, we probably maybe one of will be in the same situation. So then these individuals really need intensive and high quality home care, right? And then this actually home care is a very stressful job for caregivers or family members. So it's very challenging to provide consistently high quality home care. And in this situation, the social robots actually can make a big difference. Now they can provide, the consistent high quality home care. Yeah. The same thing happened to the people who get disabled due to the illness, and the people who are patients in the hospital, also maybe kids in the daycare settings. So it's a broad application of social robots.
Cool. So robotics can then be used in many interesting ways, but today we're going to talk about making robots feel. So why is it important then that these robots can have a sense of touch, or a prosthetic hand can have a sense of touch?
Yeah, I can start and you can probably add on. Now we know that most of robots are made of materials, hard materials like metals, right? So for robots to be able to physically interact with humans, the most important thing is to ensure safety. The robots need to ensure safety to humans when you have physical interactions. And moreover, the people also want to have a comfort interaction with the robots, right? So, and then when it comes to the home care, the robots require very quick and precise tactile feedback in order to adjust the motor control when they have interaction with the people, right? So this is why the sense of touch is important. And but today, most of the researchers are looking for sensors to detect the force and pressure, so the robots can adjust their motor control very quickly. But for social robots, actually, they need a higher level of tactile sensation. We say like a human-like tactile sensation. For instance, robots should be able to recognize what the objects, the object properties, when they get touched with different kind of objects, they should perceive the objects are soft or hard, or it's a cold or warm, and so on, or what is the material is for the objects, right?
So it's a way to keep the humans safe in that way. If they pass a warm cup, for example, they're going to know it's too warm for the human to receive, or how hard they squeeze some things so they don't hurt anyone or destroy something. Yeah,
and then they can adjust their motor control according to the properties of the objects. Yeah,
cool.
Yeah, and for prosthetics, the tactile feedback can help reduce the patient's the amputee's phantom pain, because the amputees often experience kind of pain felt part of their limbs are physically removed. But this kind of tactile feedback can help them to relieve this kind of pain and help increase their improve their user experience.
Yeah. Actually, they say there's one data set showing that because of lack of the tactile feedback for the prosthetic limbs, the people who use the prosthetic limbs will, around 30-40% of the people will abandon the prosthetic limbs they use. So if the prosthetic limbs is equipped with this tactile feedback, so can stimulate the the sense of touch now, and I think they would be happy to use the prosthetic limbs.
Then it would be more like part of your body instead of a tool.
Yes, it's increase the ownership of this, because otherwise you feel it's something external. It's not a part of your body. It would feel weird.
So then we see that there's many uses for this, both in robotics and also to getting prosthetic hands. But if we gonna move over to how it actually works, so in our body, in our tactical systems, we have specialized receptor in the skin that sends signal to our brain, and you can feel hot, cold, as you said, body position, pain, soft pressure, hard pressure, and the signals then go through our sensory nervous system. How does that work in us humans then? Because you said you want to replicate a bit what happens in the human.
Yeah, you are right. Our tactile nervous system is a very sophisticated system. It is actually equipped with different kind of receptors for capturing different kind of tactile information, and then you generate, in your brain, you generate different type of sensations in different ways. Okay, if you look at the skin, actually there are three. In simple terms, there are three families of receptors. The first family is the receptor is the tactile receptors, and tactile receptors actually can be divided into 4 types of sensors. Now, these sensors, they capture the mechanical stimulation in different aspects. For instance, pressure, vibration, textures, and so on. The second family is about the sensation of the heat. Thermal sensors, so you can feel warm and cold when you touch objects. Actually, can distinguish the object properties due to the difference in thermal conductivity, right? Using these tactile thermal sensors. The third family of receptors is about the pain. It's pain sensations. When coming to the sensing position or movement of your body, this comes to another type of receptors, which called proprioceptors. We can find these kind of receptors in muscles, joints, and tendons, right? So it's a different thing. But the different type of receptors in the skin actually can capture different information when you get touched, and then this information or signals travel along skin through different pathways to end up to the brain. And the pathways actually is a very complicated network. They have synaptic connections. So all of information will be processed and computed, highly processed during the pathways. And in the brain, you have a higher level of signal processing. So you get different perceptions and form the concept about the object you touch or grasp.
So now you're then trying to replicate this electronically. And you work on this artificial tactile system consisting of something you call an e-skin, an artificial neural network then, and a processor to just make these robotic arms and prosthetic hands be able to touch, to feel. So if we start with the electric skin, or e-skin, how does that work? You have brought something here today as well.
I brought a prototype of our e-skin here. So e-skin is short for electronic skin. Basically, it's an electronic device that translates information about touch to like temperature or pressure to electrical signals, such as voltage or currents. So it basically consists of an array of sensors, tactile sensors. And actually, there are many different kinds of sensors depending on their working principles. Here we use the sensors that takes advantage of triple electric effect. So basically, the sensor can detect the surface charge on the object's movement. So when the object touches the sensor will output changing voltage to reflect the conducting pressure. And in our work, you can see we designed a hand shape e-skin, we have 64 different sensors distributed across the whole hand. And interestingly, we have much smaller sensors on the fingertip, but with higher density. But at the rest of the hand, we have much fewer sensors, but with larger size. It's exactly the same as the receptor distribution in our real hand.
Yeah, because you feel more on your fingertips than you do on your palm.
Yeah, exactly.
Okay, cool. So I read then in your recent paper in Science magazine that to take all this information, you use new coding, new way of processing all this that is based on spikes from the sensors, and that this is much more efficient than earlier solutions. And can you explain a bit what is spike-based programming, what that does?
Spike-based coding is a fundamental way. That's how our biological nervous system processes signals, processes the information. So we can take the tactile nervous system as an example. As Zhibin said, when object touches our skin, the receptor beneath the skin will convert the touch, convert the pressure into electrical signal called the receptor potential. And the tactile information is encoded in the amplitude of the receptor potential. But in our nervous system, there's a group of neurons called the sensory neuron. This neuron converts the receptor potential to spikes. Spikes are brief electrical pulses. We also call it action potential in neuroscience. These spikes have a constant period and also duration and also amplitude. Instead of coding information in the signal amplitude, spikes code information in the timing when it occurs, when the spike generates. So this kind of coding strategy can bring some benefits. First, the spike coding is sparse coding. That means the sensory neuron at most moments are at the resting state without firing any spikes. Actually, the sensory neuron works like kind of filters. It filters out the redundant information and represents the complex tactile information using as few as spikes as possible. And by this way, it makes the whole nervous system, more energy efficient. And secondly, the spike coding is a kind of temporal coding. It's very sensitive to the dynamics of signals. So in our research, we found that most tactile information are encoded in the timing of first few spikes of a group neurons. So this feature helps the system could extract the tactile information very fast. Yeah.
So if I understand it correctly, then that when neurons fire, then send up a signal that consists basically of pulses, or spikes in that case, and that you are mimicking this body's own signal system to do it in electronic form.
Yeah.
So when you then receive the signal, how will you know if the hand or the glove in this case is holding an apple or an orange, for example? You said something about the timing of the signal. So what differs in the signal from, for example, apples and oranges?
Yes, that's
look very similar.
Yeah, that's a very good question. So when our hand holds an object, we can see that first, the shape is kind of different. So that means when we grasp an apple or an orange, different set of sensors on our hand or on the e-skin will be activated. That's the first difference. The second difference is that we can see their size in most cases are different. So that means even we fully grasp the object and the same set of sensors are activated, but the sequence and the relative timing of each sensor got activated is different. Thirdly, when we grasp the object, we can feel its stiffness. For harder objects, when we grasp it, our force increases very quickly in a short period. That means the neurons will generate more intense spikes in a very short period. So if we put all these differences together and like the difference in shape, difference in size, and difference in stiffness, we will observe a totally different in the spike timing, in the timing when the spikes generate of a group of neurons. And that's the basis how our nervous system to classify the properties of different objects.
So
may I add some more comments? We use spike timing to encode or decoding the signal. Actually, there are additional advantage, but as a spike, actually is quite narrow. It's only 1 millisecond in width, and the amplitude could be in a biological spike is 0.1 volt. But for electronic circuits, we can adjust it. There's no problem. But using the spike timing coding, there's an additional strength, which is robustness, which means you see our electron skin actually is quite rudimentary. We use foldable substrate. So it's not conformal, it's hot conformal, and we apply to the glove. So every time you grab objects like a sphere, like an orange and apple, the skin cannot really conformally attach to the surface. So every time you grasp, you can actually generate a large variation in data. But even though this system actually still able to classify different objects at very high accuracy, over 90%.
That is pretty amazing. That even though you have just kind of added it to a gardening glove, it still works so good that it can see the difference in apples and oranges. So we can just imagine how good it's going to work if you integrate it in a robotic hand or in a prosthetic hand. That's going to be... So how do you then develop something like this? Do you test it on different things? I mean, you put it on a garden glove, I suppose, because you want to try and test. And do you train your algorithms in a way with this?
Algorithms is an essential part of our system. And when to train the algorithm, first we need to create a data set. So basically, we have 4 different people. Each of them wears gloves and grasp different objects. We have 22 objects that are ordinary in our daily life, like apple, orange, banana, pens, and Moses, and some tools. And for each grasp event, we record the output from our artificial neural circuits, and then we will create a data sample. And because we have 4 different people, 22 objects, so finally we create an object data set with more than 4,000 data samples. And then we use this data set to train the algorithms. We have had a very close partnership with HR, the team at the same department. They develop the algorithms and train the algorithm and test it, found it has a very high accuracy. As Zhibin said, even the data sets have a large variance because we have different peoples, and each people have their own used gesture to grasp the objects. And finally, we test the algorithm with real-time grasping, and it also performs quite good.
Cool. So you work together then with IT department as well. And you mentioned that you then use machine learning, and that connects a bit to today's Nobel Prize that was announced just before we went live here. But I managed to write down John Hopfield and Geoffrey Hinton, who got the prize for foundational discoveries and inventions that enable machine learning with artificial neural networks. How does that connect to your research? It's pretty close to your field.
It's an interesting question. Also comment. Artificial neural network actually is a model for machine learning. So this is architecture, and basically then you use a so-called gradient descent, computed by backpropagation process. So you optimize the neural network in order to perform what you want, right? And we take this, but we use a new type of artificial neural network. It's called the next generation artificial neural network. It's called spiking neural network, which is different from the conventional artificial neural network. Is that the conventional artificial neural network use the analog real value signal as the information carriers, but for spiking neural network use spikes. As Libo said, spike usually is constant in width, it's very narrow, and the amplitude is constant. So one spike is considered of an event. There's no feature, right? So the timing of spike carry information. And then when you use a spike as the information carrier, fed into the neural network, it's a spike neural network. The problem for the learning is that backpropagation cannot be used directly because the spike cannot be computed derivatively. You cannot get the derivative from spikes. So you have a different approximation method. So our collaborator, Asha Osadika, I don't know if you have pronounced it right, from signals and systems at the same department. So they work on this. Yeah.
Cool. But how will this then communicate with the brain if you have it? I mean, for a robot I can kind of understand that you use, the whole thing is programming. But if you want to put this on a prosthetic hand, then it's going to somehow be able to communicate with your brain. How is that possible?
Yeah, I think this is a critical question when it comes to the real application to benefit humans, but patients. It is true that it's still very challenging to integrate prosthetic devices with the brain. And if we will come to the specific problem, is that how to deliver the signals from the prosthetic devices into the appropriate neurons in a right way. This is today is very challenging, and actually, as our collaborator in the project is doing this. So yeah, this is on the way, but it's challenging. Yes, yeah, definitely.
There is an UppTalk on brain-machine interface, an earlier UppTalk that you can find on the webpage as well. Brain-machine interface in the age of cyborg, with a colleague of yours, Robin Augustin. Are there any additional uses for this technology? I know you talked about how it can be helpful for people with neurological symptoms and disorders like Parkinson's disease or stroke patients. How would that work?
Yeah, this is our vision about the application of the artificial tactile systems or our devices. As I said, it's challenging to integrate devices directly with the brain, but there's an alternative approach. For instance, we can imagine we can develop a highly intelligent robotic prosthetic limbs. So this prosthetic limbs is able to do complicated or precise tasks according to patient's intention. Now the question is come to how to read and decode the intention from the brain signals. I think today there's some technology that's available. Then the second question is how to integrate the so-called cognitive integration of the prosthetic limbs and the patients. So I think there's some way to go.
But for these other neurological diseases, then it could maybe be like detecting if someone is about to fall or detecting if someone is shaking a lot or something like that, and then be able to help that person Do I understand it correctly?
Yeah. Then the prosthetic limb, robotic prosthetic limbs, it should be able to detect the tendency of care, and the patients is going to fall and need help immediately, and react precisely to help. So this robotic prosthetic limb should be highly intelligent, and for this it's required the high level of rapid feedback, sensory feedback, tactile feedback, visual feedback, and so on for this.
So our time is running out, but what I take with me from this is that there are amazing things that is ongoing, and there's a lot of programming and things on the backside of this that we don't see when we see these amazing things, but it's very, very important to make them efficient and safe. And that this is also then connected to today's Nobel Prize, which is pretty cool. Are there any additional things you want to say before we close today's session?
I think one thing I would like to say is somehow like a take-home message from this talk. One is I think some years from now, like 10 or 20 years from now, I believe the humanoid robots who can really work, interact with the people, so people can get the safety and the comfort and so on, will come true. This is my belief. The second thing is that I believe that neuromorphic engineering actually is a very powerful approach. For instance, in our case, now we use very lousy sensor. Now, if you look at the individual sensor, it's lousy. No one says it's useful. But if you use a neuromorphic approach, they give us surprise.
Really cool. Thank you so much for today. In 2 weeks' time, on October 22nd, we will meet Associate Professor Lina Mtwana Nordlund in a conversation about how global collaboration can contribute to reliable forecasts of the future of the world's oceans. That conversation will be in Swedish, so don't miss it. And thank you so much for listening today, and welcome back in 2 weeks.